All right, folks, this is Mr. Whitmire. We're going to get into our review for the second benchmark here. Second benchmark review. I also have this, well, it's also available electronically, so you can look at it on Performance Matters as well, but you could get locked out, so that's why I'm getting you this per paper test too. All right, so we're going to go really quick again, so please just rewind if you need to, and I'll try and explain things as thoroughly but as quickly as I can because I got a lot to get through here. All right, and feel free to jump around in this video to whatever you need, okay? All right, number one, graph of g of x is translation to the graph of f of x. Sorry, graph of g of x is a translation of the graph of f of x, right? So here's f of x. G of x is translated from f, all right, where point R maps to point T. Okay, they don't really need to give us this information here. We could also just look at the vertices too, all right, how the vertex changes. They're going to change in the exact same way. So let's just see how it changes, right? To get from R to T, we have to go right 1, 2, 3, 4, 5, 6, 7, 8, 9, and down 1, 2, 3, 4, 5, 6, 7. So right 9, down 7, okay? So first of all, let's focus on the down 7 part. The down 7 part, right, those are the numbers that are going to be on the outside here. Now, only two show down 7, and that is the minus 7 out here, minus 7 right here. So we can get rid of this one and this one right away, okay? Now, we also need to do right 9, and here's where it gets tricky, right? The number that's in with the x, that does affect left and right, but it does the opposite of what you'd expect. So that plus 9 there, it actually is moving left 9. This one is moving right 9, so that is our answer. That's what we want, or I should maybe fill it in or whatever. You get the idea, okay? All right, number 2. A scientist is studying bacteria. The population of one strain of bacteria can be modeled by the function f of t equals 20 times 1.03 to the t, where t represents time and days. Explain the function in the context of the problem. So the population of the bacteria is, so here blank by blank percent each day. So this is the changing, right? And by how much percent each day it's changing. So we go up here to our exponential function here. We know that this 20, that's our a value, which is the initial amount. Our b value there, the growth factor, is 1.03. Since it's bigger than 1, that means we should be increasing. And then by the percent here, remember b, when it's a growth, b is equal to 1 plus r here. So for our case, right, 1.03 equals 1 plus r. Subtract 1 from both sides. You get r equals 0.03, or as a percent, 3%. Okay, the population of bacteria at the beginning of the study is 20 cells. Again, because we started with 20 there. Okay, the number 20. It's our a value. Okay. All right, number 3. Given f of x equals 4x to the 5th minus 3x squared plus x to the 4th, and g of x equals that, perform the indicated operations, f minus g. So we're going to take our function f here and we'll subtract g. So I have 4x to the 5th minus 3x squared plus 2x to the 3rd. And we're going to subtract the quantity 5x squared minus 8x to the 5th plus 2x to the 3rd. Okay? When you subtract, oops, I forgot. Ends there. When you subtract a polynomial, I like to change it. You distribute the minus sign. So I change it to add, and then I just make all of these opposites. Okay? And now we'll just combine like terms. Okay? 4x to the 5th will combine with the 8x to the 5th to make 12x to the 5th there. The next term we want to look for is an x to the 4th term. So let's see here, x to the 4th, x to the 4th, x to the 4th. Oh, I missed writing down an x to the 4th term. What did I write down here? It should be plus x to the 4th. Oh, I must have written down some g there. So sorry, f of x was 4x to the 5th minus 3x squared plus x to the 4th, and then g of x is the 5x squared, the 8 of x to the 5th, and the 2x squared. Okay. So x to the 4th, well, there's just one of those, right? So it's just one. We took care of that one. All right, x cubed, there's one x cubed term, and that's negative 2 is its lead coefficient. And then we have two x squared terms, negative 3 and negative 5. That makes negative 8, x to the 2nd. Okay, and there's our coefficients. Right? Number 4, factor each of the quadratic expressions, select the appropriate factors for each expression, select all that apply. So here we're going to factor this thing. Okay, so first thing I want to look at there, is there a GCF? The answer is no, there's no GCF there. But we can then do our AC method. So 2 times 2 will give us 4. I need two numbers that multiply to positive 4, but that'll add to make negative 3. So two numbers that multiply, to make negative 4, sorry. 2 times negative 2 there. Sorry, it's negative 4. Okay, so two numbers that multiply to make negative 4, but that add to make negative 3. And that's going to be negative 4 and positive 1. Okay, so then we will use factor by grouping here. We're going to break up that middle term using these two numbers, so minus 4x plus 1x minus 2. Group. From the first group, we can take out a 2x, and I'll left behind an x minus 2. From the first group here, we can take out a 1, and I'll leave behind an x minus 2. And then they have an x minus 2, and then the 2x plus 1. Okay, and x minus 2, 2x plus 1. So 2x plus 1, check. X minus 2, check. Okay, those two. Next one here, I do have a GCF. I can take out a 3. Both of these are divisible by negative 3, so I take a negative 3 out. I'm left with x squared minus 16. X squared minus 16 does factor, okay? It's quadratic, right? Now, it's missing its middle term, so you can think of it like this. X squared plus 0x minus 16, okay? And then you're looking for two numbers that multiply negative 16 and add to make 0, so that'll make x plus 4 and x minus 4, okay? So there's our negative 3 down there. Check, we got that. The x plus 4, check, we got that. And x minus 4, check, we got that. Remember that this here is also called a difference of squares. It's a squared minus b squared there, and that's equal to a minus b times a plus b. Okay, so here it's x squared, right? And then the 16 is really 4 squared. So you get this x minus 4 and then x plus 4. Okay, there's our factors. All right, part B, solve the following equations. Then select the correct zeros to the appropriate quadratic equation, select all that apply. So check it out here, same thing as in the practice, right? This and this are the same quadratic. So we can use the factored form there. So it's really x minus 2 times x plus 4, excuse me, equals 0. Okay. Wait a minute, what? What am I looking at here? Sorry, that's the factored form. X minus 2 times 2x plus 1 equals 0. My mistake there. Okay, set each factor equal to 0. And so x equals 2, check, and 2x plus 1, so x equals negative 1/2, check. Okay, you could have used the quadratic formula here too if you wanted to, since it is equal to 0. That's another option you have there. You can also graph this and see where it crosses the x-axis. That's another way to do it. These two are the x values where they cross the x-axis, like the 0 command and stuff. Your choice. Anyway, this one also factors. It's the same problem, so we can just go ahead and use negative 3, x plus 4, x minus 4 equals 0. Set each factor equal to 0. Negative 3 will never equal 0, so it's just really x plus 4 equals 0 and x minus 4 equals 0. And so we get x equals negative 4 and x equals 4. 4, negative 4. Check, check. Number 5, determine the coefficient of x that would allow the following expression to be factored. Okay, so let's see here. Woof. How are we going to figure this one out? All right, so let's do the AC method here. So 4 times negative 6 will give you negative 24. And we need two numbers that will multiply to make negative 24, but that will add to make some of these here. So let's just try 25. So let's see here. To multiply to make a to add to make a positive 25. Let me do this way. Maybe our negative 24 we can break down as negative 1 and positive 24. That will not add to make 25. We could do 1 and negative 24, but that also will not add to make 25. And everything else besides that, well, it just won't be big enough, right? 2 and negative 12, negative 2 and 12. Okay, so 25 I'm pretty sure we can just throw out there, right? 5, well, let's see here. We could also do 3 and negative 8 or 8 and negative 3. And aha, 5 works. 5 works. Okay, because the 8 and the negative 3 would add to make the 5 there. Okay. Goodness, yeah, I'm concerned that one other thing will work here, but perhaps not. Well, anyway, 5 works, so we know that's got to be the answer there. Okay? All right, classic border problem. Jacqueline has a garden in her backyard that measures 8 by 12 feet. There are the measurements. She wants to create a uniform path of width x around the garden. So again, draw in those x's if they help. Okay, write the expression in terms of x. Expression, so no equation there, to model the total area of the garden space with the walkway included. So this distance, right, if this is 8 feet from here to here, we're going to add an x on here and an x on here, so it's 2x plus 8 is that total distance there. Likewise here, if it's 12 there, and we have an x this way and x this way, so it's going to be 12, or 2x plus 12 here for this whole length as well. Okay, so the expression for the area then, we multiply. 2x plus 12, 2x plus 8. You do not need to multiply it out. It does not say that you need to have it in standard form, okay? Then it says, find the border width when the total area is 285 square feet. Total area. So in other words, we want to take this and set it equal to 285. And make sure you do that work, though, down here, because this is the question that has this in it. Okay, we're going to multiply this out. So 2x and 2x makes 4x squared. 2x and 8 makes 16. 2x and 12 makes 24. So 16 and 24 makes 40. And then 12 times 8, 96. Okay. Now at this point, actually at this point, we could have graphed this. Okay, you're going to have to adjust your calculator. You have to adjust your y max so you can see that 285 horizontal line there. And then just find the x-coordinate of the point of intersection of the quadratic here and this number. Alternatively, we can multiply this out, subtract the 285 over. I get negative 189. And then we could use quadratic formula at this point, right? Or we again could use our graphing calculators and just try and see where this is equal to 0, okay, by just finding the zeros there, okay? I'll show you quickly how to do it with the graphing calculator, and then maybe I'll try and quickly do it with the quadratic formula too. Okay, here it is graphed. Okay, so I can see here that I've got an answer right there. So I'll go to 0. Okay, to the left of the 0, to the right of the 0, hit enter. 3.5. 3.5 is the answer there. Oop! In terms of inches, be careful here. So I got x to be 3.5 feet, which I have to multiply by 12 to get inches, so 42 inches. That's annoying that they make us do that. Please do not get caught up on that, folks. It gives us feet. We need to rewrite it in inches. Okay, so 42 inches is our answer there. Okay, now, really quickly, if you want to do the quadratic formula here, it'll be, I'm going to do it up here. I don't have enough space. Please don't do it up here in your work, though. Make sure you do it on your answer mat or something like that. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, you type that discriminant in, 40 squared minus 4 times negative 189, 4624. Okay, so that discriminant simplifies to 4,624, and we're all over 8. Okay, and then square root of 4,624 is 68. So you have two answers, negative 40 plus 68 over 8, and then negative 40 minus 68 over 8. We can go ahead and throw out the negative 40 minus 68 over 8 because that's going to be negative, right? We don't want negative x value here. It wouldn't make sense in the context of a width of a walkway. We'll do negative 40 plus 68. We get 28. Divide that by 8, and you get your 3.5. Okay? Again, that's in inch or feet. I mean, so you got to convert that to inches, right? And multiply everything by 12. And you get 42. All right. 7. Table shows 3 systems of linear equations. Indicate whether each system of equations has no solution, one solution, or infinitely many solutions. No solution, one solution, infinitely many solutions. By selecting the correct cell in the table, select only one box per row. Okay, boom, right here. This one, okay, with the way it's set up, we already have 1 solved for y. Let's go ahead and solve this top one for y too. So 2x minus y equals 10. Subtract 2x from both sides. We get negative y equals 10 minus 2x. Divide everything by negative 1. Okay, and we get y equals negative 10 plus 2x. Okay, so we'll graph this one and this one. Now if you look here, negative 10, there's negative 10, 2x, there's 2x. So in other words, these two lines are going to be the same. Oops, I'm off the screen. Sorry, I didn't show you guys. So again, I took the 2x minus y equals 10, solve for y. So subtract the 2x from both sides. These are not like, so I rewrote 10 minus 2x, divide everything by negative 1. So I get y equals negative 10 plus 2x. But that is the exact same line as the other line. They're the same line. What does that mean? Infinitely many solutions. If you don't believe me, go ahead and graph them both. When you graph both of these, you're going to see you get the same line. And so they intersect everywhere, which means there's infinite solutions. This one's already ready to be graphed, so let's go ahead and graph it. All right. You can see here that the slopes are different, and so we should expect to have them intersect, right? That's pretty straightforward, I think. So we graph there. There's one line. There's the other line. 1 point of intersection, 1 solution. All right, this one right here, You could solve each equation, top and bottom, again for y, and graph them both, your choice, or we can use elimination here, right? I can see that I can eliminate the x's if I just multiply this top one by a -2, and multiply this by -2 as well to balance it out. And so we'll end up with -2x plus -4y equals -4, right? If I distribute that -2 to both, and then that times -2 gives us that. And so the -2x and the 2x will cancel. The -4y and the 4y will cancel. So I'll have 0 on this side, and then -4 and 6 makes 2. When does 0 equal 2? The answer is never. Okay? If you were to actually solve each one of these equations for y, get them in slope-intercept form, you'd see that the slopes are the same, but the y-intercepts are different, indicating parallel lines. The lines do not intersect. All right, number 8. Given the systems of inequalities below, determine which of the following statements is false. Okay, again, false. Please make sure you only pick the false statement here. Okay, so -4, 0 is the solution to the system. How can we check? Well, we can plug it in. So let's plug it in here. If I plug in -4, 0, -4 goes in for x, 0 goes in for f. So I get 0 is less than -4 plus 6, which simplifies to be 0 is less than 2. Check, that's right. All right, let's try this one. 0 is less than or equal to -2 times -4 plus 8, which then would simplify to 0 is less than or equal to 8 plus 8, which is 16. Is 0 less than or equal to 16? Check, it is. So that is a true statement, so it's not the right one. We need a false statement here. Okay, we'll try this one. Okay, I'm going to do this one mentally here. So -4 plus 6 is 2. 2 is not greater than 2, but it says it's not a solution to the system. So again, that's a true statement. -4, 2 does not work in here. That's what this says is. That's what this is saying. And so in other words, that's a true statement. Okay, let's try this next one. -4, -1. -4 plus 6 is 2. -1 is less than 2. Check. I'm going to plug it in here. -2 times -4 is positive 8 plus 8 is 16. -1 is less than or equal to 16, so check, that one works. So in other words, we don't want it. We only want the false one. So hopefully this one fails. Let's check it out. -4 plus 6, that'll be 2. Is 8 less than 2? The answer is no, so it's this one. That is our answer there. Okay. Number 9. Diagram below shows the dimensions for a backyard patio that includes a seating area and an outside kitchen where x is measured in feet. So seating, outside kitchen. Okay? Create a polynomial to represent the combined total area of both sections of the patio, so seating and outside kitchen. Simplify the polynomial and write it in standard form, fill the blanks in below. All right, so for this, right, the area of the seating is going to be x plus 6 times x plus 8, which we have to simplify, so I'll go ahead and do that. We get x squared, right, x times x, 6x, and x times 8. Let me do it this way, sorry. X times 8 is going to be 8x, but 6 times x is going to be 6. So 8 and 6 make 14x when you combine like terms, and then 6 and 8 make 48. Okay, so there's the area of the seating right there. Now, for the outside kitchen, we know that this distance right here is 2x, but it's going to be 2x times, we need to find this full length here. Well, from here to here is x plus 6, because that's what we're told right here. If this is x plus 6, then this will be also x plus 6. We have to add on to it then 1.5. Which then really gives us 2x times x plus 7.5, and then we distribute. So we'll get 2x squared plus 15x. And then to combine those together, well, the x squared and the 2x squared will give us a 3x squared. 14x and the 15x will make a 29x. And then the 48 has nothing to combine with over here, so it's just 48. And there's your answer in standard form. All right, next. Part B, the family has decided to also add a pool with an area. So this is the same problem we were talking about earlier. The family has decided to also add a pool with an area that can be represented by the expression 2x squared minus 11x plus 5. Match each expression with the appropriate description. So in this situation, we're just going to look at this polynomial. We're forgetting about the other stuff, I think. Yes. So what's the lead coefficient of this? The lead coefficient is 2, right? It's the coefficient of the highest powered term. The constant here, that's the 5, so that matches to the 5 right there. The factored form, okay, so in other words, what is this factor to be? Well, if you just look here, there's only one thing that looks factored, so it's got to be that one. And then the zeros, well, that's what happens when you set these equal to 0 and you solve, you get the 1/2 and the 5 there, okay? So not really any hard work there. Ooh, pretty pattern. All right, number 10, a popular spot to cliff jump into the ocean is at the Spitting Caves of Port Lock in East Honolulu, Oahu, okay? Interesting. Anyway, the cliffs are 65 feet tall. The height h of the divers at any time t can be modeled by this, where v sub 0 is the diver's initial velocity, vertical velocity, and h sub 0 is the diver's initial height from the water. The initial vertical velocity of the diver is 16 feet per second. Now, keep in mind here, the diver is going to be jumping from a height, and the diver is going to go up first before it goes down, right? Because they're going to jump off and down. They're not going to just fall down, okay? They're going to jump up and then go down some, okay? So the curve's going to look something like this, okay? The diver will hit the water at blank seconds. So let's see here. We need to figure out what this function is. So h of t equals negative 16t squared plus initial velocity. We were told that 16 feet per second. Plus, what's the initial height, though? The cliffs are 65 feet tall. The diver will hit the water at blank seconds. Okay, so notice we want to set this equal to 0. Now, I recommend using your graphing calculator here. So in other words, type this in your graphing calculator. Okay, so negative 16t squared, we have to use x's, of course, for this, plus 16x plus 65. All right, we'll graph it. Now, I can't see the whole graph, but I can see the 0. So I'm not going to worry about adjusting just yet. I'll just go ahead and use the 0 command. Okay, move to the right here until I can see my cursor. So there I am, to the left of my 0, hit enter, and I'll go move to the right. Now I'm to the right of my 0, hit enter, and I'll go back for the guess. 2.576656. Now it says round to the nearest thousandth. So that means I got around 3 decimal places. 0.577, because the 6 would round up there. So 2.577 seconds, right? You don't have to put the word seconds in. It's already there. The diver will reach a maximum height of blank feet. Okay, maximum height. Now, to see the maximum height, I do need to go to my graphing calculator. I got to adjust up, because I can see the curve goes up higher here. So window. Let's see, 65 is the height of the cliffs. So I'm going to go at least 65. I'll go up to like 80. Let's try 80 and see what we see. There we go. I can see the height of the diver, maximum height. So second trace, maximum, left, enter, right, enter, guess at the top, enter. 69 feet. Okay, 69 feet. Okay, and that's all for that question. 11, you have a circular pool with a water surface area, circle, area, 475 feet squared. You are purchasing a solar cover, and the catalog lists the sizes by diameter. So we need to find the diameter of this. The manufacturer recommends placing an order for a size larger and cutting off the excess. So in other words, round up, okay? So area for a circle, pi r squared, okay, 475. And for the area, divide both sides by pi. And I get like 150, let me just go ahead, 151.197. That's r squared. Square root both sides to get rid of the square. Can I get like 12.296? Okay, but that's a radius. I don't want a radius. I need the diameter, right? It's the diameter of the pool cover. The radius is half the diameter. So in other words, to get the diameter, we'll do twice the radius. Okay, and I get then 24.592. Now, if I order a diameter of 24, I'm not going to have the big enough pool cover. So I'm going to order a diameter of 25 feet. Okay, and then round that up there. Okay, diameter 25 feet. A large city is interested in crime rates and prevention. They have gathered the following data on the number of crimes per year, C of t, and number of years since 1990, t. Okay, so this is t is number of years since 1990, C of t is the number of crimes per year. Okay, complete the following statement. The model is best represented by linear, exponential, quadratic. Well, let's look at our equation here. We had 13,996, then 9641, then 685, 6587, 4575, 3100, 274. So we see we're going down every time here. So it can't be quadratic, because quadratic would be with increase and decrease here. Okay? Let's look at linear, exponential. Linear. If it's linear, we're going to go down by the same amount each time. Now, I can see right away that to go from 13,996 to 9641, and then down to 6587, and all the way down here, we're going to go from 1515 down to 854. There's no way that this distance, right, from 13,996 to 9641 is the same as 1515 to 854 there. Oops. This and this, they're definitely not the same. Oh, we do need to be careful. Shoot. This is frustrating. Look at the time here, folks. 0, 2, 4, 6, 8. Then they go up by 1. So we're going up by 2, up by 2, up by 2, up by 2, up by 1, up by 1, up by 2, up by 3. So we actually got to be kind of careful here. All right, let me find the actual difference here. Okay, I get 4335, or 4355, sorry. And then to go from here to here, it's 3054. Okay, so here we can safely say that it's not linear because even though, yes, we're going up by 2 years, this time we're going up by 2 years, this year's we're going up by 2 years, right? And for this 2-year span, we went down 4,355, but for this 2-year span, we only went down 3,054. So it cannot be linear, so it must be exponential, okay? And then because, well, not because there's no change, not because there's a common difference, there must be a common ratio. So let's see if I can figure out what that ratio is. So I'll take our second thing and divide by our first thing. Okay, so 9641 divided by 13996. I get that. Now let's take that and multiply by the 9641. So that's our common ratio. We get 6641, which is kind of close to that. I mean, even that's not really a common ratio. So that's kind of frustrating. But again, these are like real numbers. So it's better modeled by exponential than linear for sure, though. Okay, what is the equation of the regression model that you selected? So now we're going to have to come up with the equation. That's the stat edit. Okay, clear out your list 1 and list 2. Remember, clear button. And then type in your, 6, 8, 9, 10, 12, 15. And you have to type in your L2s here. Okay, stat calc exp reg, because we chose exponential regression. Okay, so there's our curve, 15,115 point, round to the nearest hundredth, so to 26 times, and then 0.81 to the t, and c of t here. Okay, how well does the model how well does the model you found in part B fit the data? Use mathematics to support your answer. So here you can just test a couple of points. So let's just try, well, for example, we can test our first point, right? So they start at different values when t is 0. And by year 15, or not year 15, by, well, let's see. I'm going to look at the end point too here. So 15 years later would be 2005. So let's see. I'll plug in 15 there for t. So 15, 115.26.81 to the 15. 640, and then 854. And by 2005, the model is still a little higher, or still is whoops, it's not still, it's now a little lower than actual at 640 people. Okay, when the model predicts 640 people, the table predicts actually 854. So something like that to describe it. All right. Keep rolling here. 2012, the population of Frederick was 66,387. 2013, the population increased to this. Okay, assume the population was increased linearly since 2012 and will continue to increase at this pace. What will the population be in 2014? So in 2012, we had 387, and in 2013, 66893. You would then see what we're going to add by there. So 506 people were added, okay, between 2012 and 2013. So if it's linear, we expect to add another 506, which is kind of crazy to think about that it would be, so precise. But we're going to have to do it for the model. 67,399 then for 2014. Excuse me. Okay, now suppose the population is increasing exponentially. You choose the function that represents the population in terms of t, the number of years since 2012. So 2012 is our starting point. So we're going to use 2012's initial population there of 66387 as the starting point. This one has 66387. This one has 66387. So we're going to throw out the other two automatically. Okay, and then really we don't even need to see what the percent growth is because we know we're growing. So it's got to be this one, right? This one's a decay. Oops, sorry, this one is a decay, right? It's not bigger than 1. It's 0.008. So that one's out. This one's in. It's got to be because that's bigger than 1. Now, if you want to be sure, okay, we'll take our newer population and divide by our older population there, okay, and we'll see what decimal we get. And I get like 1.0076, so that would round up to 8, and so there's your 1.008. That's what we're multiplying by every time there. Okay. In part C, using the model you found in part B, what will the population be in 2015? Round your answer to the nearest whole number. Now in 2015, all right, we don't put in 2015 for t, right, because the number of years since 2012 is t. So 2015 is t equals 3, so we'll plug 3 in for our t there. So we'll do 66387 times 1.008 to the 3, or about 67,993. And round to the nearest whole number. Okay, no parts of people, please. Population of Hagerstown, MD, can be modeled by the function h of t equals that in terms of year. Now you can see here we have a decay, right? So, okay. Explain what the value 0.99 means in the context of the problem. The 0.99 represents a decrease, right, because it's less than 1, of not 99, 1% of the population in Hagerstown, right? B is 0.99 here, which is equal to, in this case, since it's a decay, 1 minus r. Okay, subtract 1 from both sides, and you get that r is, or negative r, right? Negative r is equal to negative 0.01, which means r is 0.01, which is 1%. 1%. Okay. On to the back. All right, looking at this function, what's the y-intercept of the function? Y-intercept, that's where the graph crosses the y-axis. It means we'll have a 0 for the x-coordinate, and then we'll have to find the matching y-coordinate. An easy way to do this is just plug in 0 here. So plug in 0 for your x, and you see you're just going to end up with 40. So you get the point 0, 40. Okay? If you don't like that, you could also graph it on your graphing calculator and see where it crosses the y-axis. Or you can use your table, too, on your graphing calculator. Let me just type that in here real quick. Okay, a table, and see where y is 0, you get, or sorry, where x is 0, you get y is 40. Okay, you can also look at the graph too. It'd be hard to see potentially there, but there you can see it. All right, but you have to kind of figure out, you can maybe try using trace. Oh, there it went. Snapped right to it, 0, 40. How about that? It's kind of nice. What's the vertex? All right, the vertex, well, I can see it right here, so you can do second trace. In this case, it's going to be the minimum, right? So I'll go to the left because it's like the parabola opens upward. So to the left of the vertex, hit enter. Then arrow over to the right of the vertex, hit enter, and then down towards the vertex for the guess. So we're going to call that 7. Okay, it's a rounding error in the calculator's part. 7, negative 9. Okay, if you don't want to use your calculator, remember that the x-coordinate for the vertex will be negative b over 2a. And so in this case, it would be negative 14 over 2 times 1. Negative 14 is 14 over 2, which is 7. Then you would plug the 7 back in here, f of 7, and you get 7 squared minus 14 times 7 plus 40, which equals then negative 9. And so there's your 2 points right there. Okay, letter C, what's the axis of symmetry? Easy, it's this x-coordinate of your vertex. What are the x-intercepts of the function? Okay, pretty easy to do. Option 1, you could factor this thing. So x-intercepts or the graph cross the x-axis. So you're going to have something, 0. So we're going to set our function equal to 0 here. Quadratic formula would work here because you're setting it equal to 0, right? And it's quadratic. Or you could try and factor. This does factor. You're looking for two numbers that multiply to make 40, but add to make negative 14. That's going to be 4 and 10. Negative 4 and negative 10. So this equals x minus 4 and x minus 10 equals 0. So x minus 4 equals 0. X minus 10 equals 0. So x equals 4 and x equals 10. So 4 and 10. And again, since our x-intercepts, their y-coordinate will be 0. Okay? Part B, graph the function. Well, that's easy. We've got 4, 0. We've got 10, 0 there. Okay, 7, negative 9 is the vertex. That's easy enough. Okay, if you want to get some more points, you can plug in some other things. 0, 40 won't fit, so we're not going to worry about graphing that y-intercept here. Let's go ahead. I'll just go to my table since I got my table up. Let's see here. So 6 is negative 8. 8 is negative 8. So 8, negative 8. 6, negative 8. Okay, something like that. Let's just go up 5, negative 5. And then 9, negative 5. And so you get the idea. You can just kind of connect the dots there. Okay, voila. Use a table if you need to. Okay. 15. Marin works during the school year as a babysitter and a tutor. Marin babysits for $4 per hour. Marin tutors for $7 per hour. She is only allowed to work at most 13 hours per week. At most means no more than that, right? So less than or equal to 13 hours per week. She wants to make at least, that means greater than or equal to $65 per week. Let X represent the hours she babysits and Y represent the hours she tutors in a week. Using the graph below, select the letter of the solution area that correctly models Marin's work time during the school year. So is it A, B, C, or D? Well, let's think about this here. For the amount of work that she can do, let's say that X is babysitting hours and Y is tutoring hours. Okay, so X plus Y, right, is at most less than or equal to 13, right? Tutoring hours plus babysitting hours plus tutoring hours, that's maybe less than or equal to 13. But then at the same time, she makes money. She makes $4 per hour of babysitting, and she makes $7 per hour of tutoring, and that's she wants to make at least 65. Okay, so you can see here, if I wanted to graph these, okay, I would have one, well, this one I could subtract X on both sides. I'd have Y is less than or equal to 13 minus X. So 13 would be the y-intercept, and then a slope of negative 1. So that's this line right here. Okay, this one right here. And I want to be less than or equal to that line, so I'm going to shade below. So I'll go very lightly, shade below that line right there. Very light. Okay, and then simultaneously, though, we're going to do this one. So minus, well, the other line then must be that one. If I subtract 4x and divide both sides by 7, my inequality will not flip around, right? I'm not going to multiply or divide by a negative number, so the inequality sign stays the same direction. So it means I'm going to shade above this other one. And we can see where they overlap, right in here. Okay, you could also use a test point in each one of these regions to see which one makes these two inequalities true. That's another option, but I think the shading is the easiest. So there's B. So B is our answer. Okay. Which pairs, X, Y, represent the amount of time Marin can babysit and tutor each week? Select all that apply. So let's just check to see what fits in B. So let's try 210. So 210 works, so check. 5-4. 5-4 is an A, so no. 13-2. 13-2 is not in section B, so no. 5-8. 5-8. Now it's on the boundary line, but the boundary line is a solid line there, so 5-8 does work. And then finally 9-6. 9-6 is in region C, so no. Okay, so 210 and 5-8 work. Okay, let's take a look here. So now we're going to match these functions to their graphs. Okay, you'll notice that also these functions are all quadratic, but they're in different kind of forms. Well, actually, they're not all quadratic. Uh-oh. I think this one is supposed to have a square there, okay, because all these other ones are quadratic. Okay, so this is in vertex form. Remember that minus 3, and with the x, it shifts things right 3. That plus 1 with the y means it shifts things up 1. So we can go right 3 and up 1. Right 3 up 1 could be that. Right 3 up 1, nope. Right 3 up 1. So it's got to be graph A is f of x. Okay, that's only going right 3 up 1. Okay, you can also graph on your graphing calculator and see which ones match up too. All right, this one is in 0 form. Right? If we set that equal to 0, we'll get zeros at 1 and 3. So let's see here, 1 and 3. Oh, but this one also has zeros at 1 and 3. So we're going to have to hang tight with that real quick. This one is also in vertex form. Remember that plus 4 means we're going to shift left 4. The plus 6 on the outside means we're going to up 6. So left 4, up 6, left 4, up 6. That is this guy right here. And it's only that one. So it's got to be j of x there. Now, if we look here between g and h, right, we could, again, graph them in our graphing calculator. But look at your a value here. In g, the a value is 3, which means we should be concave up or opening upwards, right? Well, here we have the zeros of 1 and 3, but it's opening downwards. So it can't be b. It's got to be c. So g of x is c, which leaves then, by process of elimination, h of x for b. Okay? You can try factoring this, or again, just do on your graphing calculator and see that it matches up there too. Last paper. A function table is shown below. Whoop, there it is. Fill in the blanks. Function f of n, f of n, can be represented by arithmetic or geometric. Remember, arithmetic, you're adding every time, same amount every time. Could be adding a positive or adding a negative number. Geometric, you're multiplying that same amount each time. Let's take a look here. We go from 5 to 15. That's going up 10. But going up 10 more, I should be 25. Ooh, it's up to 45. So we are clearly geometric here. Clearly geometric sequence. Because it increases by a constant factor. We are multiplying by 3 every time, etc. You get the idea. Which of the equations below, or which equations are in the table above? Select all that apply. All that apply. Okay. So this one does. You can see the initial. Remember the explicit geometric formula for a geometric sequence. Explicit formula for a geometric sequence is f of n equals a sub 1. Well, I guess I should really write it. F of 1 times r to the n minus 1. Okay, f of 1, our first term there is 5. So it would be, the 5. And then we're multiplied by 3. Okay. Another way to write that would be a sub n equals a sub 1 times r to the n minus 1. That's the other notation there. So either of these, are good. I don't see any a sub n's, though, so we're not going to use that one. Then there's also recursive. Don't forget recursive. Recursive looks like a sub n equals a sub n minus 1 times 3. Or it could be a sub n plus 1 equals a sub n times 3, like that. It's always your previous times 3 then gives your next. Previous times 3 gives you the next. So let's see here. So nope. First term is 5. And there's no f there, so no. First term is 5. That's right. 3 times then the previous term. Yep. This one, check. Check that one there too. First term, and then no. So it's just these two. This one. You can see it tells you where you start. First term is 5. And then to find the next term, you take the previous term and times 3. And then here's the explicit formula, starting amount, and then 3 times the n minus 1. Okay? And that concludes. Oh, nope, no, it does not conclude. 18, last one here. Find the value of c that would need to be added to both sides of the equation to complete the square, then solve the equation to determine the solutions. Okay, so we want to complete the square here. Remember, to complete the square, you're looking to factor this to create 2 of the same factors. So we need these 2 numbers here that we don't know. They have to multiply to make c, which we'll figure that out. But we have to add to make 8. Well, what 2 numbers add to make 8 and they're the same number? Well, it's clearly 4 and 4, which makes this c, well, 4 times 4 gives us 16. Okay, so c is 16. Okay, what are the solutions? So here we'll just take our work that we already have written out for us and we'll solve it. So we know x squared plus 8x plus 16 is going to factor to be x plus 4 times x plus 4. 24 and 16 make 40. X plus 4 times x plus 4 is x plus 4 squared. Square root both sides. Now the square root of 40, that's we can break that into root 4 times root 10, and we do that because root 4 is equal to 2. So we'll have plus or minus 2 root 10. So we'll subtract 4 from both sides then, and we get x equals negative 4 plus or minus 2 root 10. So negative 4 plus 2 root 10, check this one. Negative 4 minus 2 root 10, check that one. Okay. You could also use quadratic formula. If you want to multiply this out, subtract the 40 over, you could use quadratic formula there too. It would be simplified to both of those as well. Last one, number 19, Lamar runs a series of summer camps across the U.S. The profit function P of C for the camps can be determined by the function P of C equals that, where C represents the total number of children attending the camps. This should be C's. These should be C's right here. C, C. What is the domain of the function in context of the problem? Okay, domain, in context. We're talking about children. So in other words, there should be no negative numbers. So not all integers, because that would include negative numbers. Also not all rational numbers, because rational numbers could also be negative, so not that one. So it's rational greater than or equal to 0, or integers greater than or equal to 0. Remember, rational numbers include fractions. We don't talk about fractions of children. You either are a child or you are not a child. Okay, there's no partial child. Okay, so not that, it is integers. Okay, integers. And that concludes the recording. So good luck. Please review this if you need to by rewinding. And yep, we'll just get started on our benchmark on Tuesday, which is tomorrow.